This is an AS D1 question on linear programming. The manager of a factory is planning the production schedule for the next 3 weeks for a range of cabinets. The following constraints apply to the production schedule. The total number of cabinets produced in week 3 cannot be fewer than the total number produced in weeks 1 and 2. At most, twice as many cabinets must be produced in week 3 as in week 2. The number of cabinets produced in weeks 2 and 3 must, in total, be at most 125. The production cost for each cabinet produced in weeks 1 and 2 and 3 is £250, £270 and £200 respectively. The factory manager decides to formulate a linear programming problem to find a production schedule that minimizes the total cost of production. The objective is to minimize 250x plus 270y plus 200z. Part A, explain what the variables x, y and z represent. Now the clue to that answer is in this part here, because I see 250, 275, 200, which are the coefficients of x, y and z. So that must be the number of cabinets produced in week 1 for x, the number of cabinets produced in week 2 is y, and the number of cabinets produced in week 3 is z. Okay, in part B, write down the constraints of the linear programming problem in terms of x, y, and z. So I'm going to start with my non-negativity constraint, which is the number of cabinets produced in each week cannot be negative. So x, y and z need to be greater than or equal to 0. Okay, now we'll go through each one of these bullet points here. So we've got that the total number of cabinets produced in week 3 cannot be fewer than the total number produced in weeks 1 and 2. So that inequality would be week 3, the total number of cabinets produced in week 3 cannot be fewer. Okay, so it can be the same as the total number produced in weeks 1 and 2. So that'll be x plus y. If we write it this way around, less than or equal to z, or you could think of it as z needs to be greater than or equal to x plus y. The number of cabinets produced in week 3 cannot be fewer, so it has to be more or the same as the number of cabinets produced in weeks 1 and 2. Next, we'll look at the next bullet point here. So it says that at least or at most twice as many cabinets must be produced in week 3 as in week 2. So if we take the number of cabinets that's produced in week 2, and that's going to be y, and then the number of cabinets produced in week 3, which is z, however many I produce in week 3 needs to be at least twice as many as I produce in week 2. So that means I'm going to have greater than or equal to. In other words, the amount of cabinets produced in week 3 must be at least double the number of cabinets produced in week 2. Then the next bullet point we've got here is that the number of cabinets produced in weeks 2 and 3 must be in total at most 125. So the total number of cabinets produced in weeks 2 and 3, so that's y plus z, it can't be any more than 125. The most it can be is 125, so that gives us our next inequality. So this gives us all the constraints of the problem represented as linear programming. Sorry, I mean represented as inequalities ready for linear programming. Due to demand, exactly 150 cabinets must be produced during these 3 weeks. This reduces to x plus y is less than or equal to 75, x plus 3y is greater than or equal to 150, x is greater than or equal to 25, and y is greater than or equal to 0, which are shown in diagram 1. That's going to be coming up in a moment in the video in the answer book. Given that the manager does not want any cabinets left unfinished at the end of a week, part C, and first part C, use a graphical approach to solve the linear programming problem and hence determine the production schedule which minimizes the cost of production. You should make your method and working clear. So here is the diagram 1 that is found in the answer book. So we have our feasible region here, and what we need to do in part C is to minimize, as we've got at the top, minimize the cost, which I'm going to call C, and the cost is equal to 250x plus 275y plus 200z. Now this objective function needs to be defined in terms of x and y only, and we've got the variable z. Now we're told in this part of the question that exactly 150 cabinets must be produced. So that means that the total number of cabinets x plus y plus z is equal to 150, and we can easily rearrange that to make z the subject. So this z is 150 minus x minus y, and we can use that to substitute into this x to make sure that our objective function is now formulated in terms of x and y only. So we'll put 200, and then in brackets, I'm not going to have a lot of space for brackets, so let me do it underneath. So plus 200, and the z becomes 150 minus x minus y. Right, I guess we can simplify that. So we've got 250x, and then minus 200x, we've got 50x. And then we've got 270y minus 200y, just leave 75y. And then we've got 200 times by 150, so plus 30,000. Now I could use the method where I draw the objective line and use that to find the point that's going to give me a minimized cost. That's difficult to do on something like this. If I was doing it on a camera or something, I could show that visually. It's difficult to do it like this. So I'm going to be using the vertex testing method, which is an alternative way of finding the point that gives you the minimum cost. So I'm going to start with this vertex here. So this is the intersection of the line x plus y is equal to 75, and this line here, x is equal to 25, which means that y is going to be equal to 50. Now if we substitute those values of x and y into C, what we'll get is a value of 35,000. So 35,000 pounds is going to be the cost. Okay, let's now move on to this vertex here. Now this vertex, this is the intersections of the line x plus 3y is equal to 150, and the line x equals 25. So if x is equal to 25, we've got 25 there, that means that 3y is going to equal to 125. So y is going to be 125 over 3. We'll substitute those in to our objective function here and work out what this cost is going to be. So 50 times by 25 plus 75 times by 125 over 3 plus 30,000, and that gives 34,375. And then we'll move on to the last vertex here. Now this is the intersection of the lines x plus y is equal to 75 and x plus 3y is equal to 150. So we're going to have to solve these simultaneously to work out the values of x and y. So if you subtract the equations from one another, we will end up with 2y. So I'm basically doing x minus x, and then 3y minus 2y, and then 150 minus 75. It's going to be 75. So that gives y is equal to 75 over 2. We'll substitute that in to work out what x is, and that's also going to be 75 over 2. So we'll substitute those values in and work out what our cost is, and that comes up as 34,687.5. So I can see that the one that gives us the lowest cost is the second vertex. That's the lowest value. That second vertex was the x plus 3y equals 150. Yep, that was this vertex here. So the coordinates of this point here are the values of x and y that we had. So that's 25 and 125 over 3. Now we require an integer solution because you can't make like a fraction of a cabinet. So we need to now test around this point to find an integer solution. Now if this purple dot represents this point 25, 123 over 3, we're fine in terms of the x coordinate. That's an integer value, so we don't need to look across from that, but we do need to look up or down because it's 125 over 3, which is basically 41 and 2/3. We need to look at the integer solutions either side. Now the integer solutions would be this one, the y value, that would be 41, and this value, y value, would be 42. Now I can see from my diagram that if I go down, I'm outside of the feasible region, so 41 as an integer solution is not going to be valid. So actually I don't need to do any calculations or testing, but I do need to just double check and test that this point, the 2542, meets all of the constraints, and also work out what cost that's going to give me. Okay, so let's test this point 2542. So that means that we've got x equal to 25, y equal to 42. So let's go through each of the constraints here. So x plus y less than 75. So 25 plus 42, is that less than or equal to 75? Yes, because that's only going to be 67. Let's go on to the next one. So 25 plus 3 times 42, is that greater than 100 or equal to 150? So let's work that out. 25 plus 3 times 42, that's 151. Yeah, so it meets that constraint. Is x greater than or equal to 25? Well, it's equal to 25, so it meets that constraint. And yes, y is greater than or equal to 0. Now if we did test this point here, 2541, we would find that it fails the second constraint here, because 25 plus 3 times 41 is only 148, so that fails this constraint. So this is not going to give us a valid solution. So we've now got this point here. So we should always now interpret our answer in terms of the context of the question. So what we've got, the numbers that they should produce, the numbers that should be produced. Right, so week 1, which is X, they need to produce 25 cabinets. Week 2, they need to produce 42 cabinets. Now remember week 3, and remember that the total number of cabinets they need to make is 150, and Z is equal to week 3, 150 minus the 25 minus the 43. So if you do that in week 3, 150 minus 25 and 42 gives us 83. So week 3 should be 83 cabinets. And lastly, the second part of part C is to find the minimum total cost for the production schedule. Okay, so our costs, which we had before, we worked out in part B, is going to be equal to 50x, x is 25, plus 75 times by y, which is 42, plus 30,000. Let's calculate that. And that gives a total of 34,400, and units 34,400 pounds as a minimum total cost.